Section 2.2. The discovery of atomic structure. Dalton based his conclusions about atoms on chemical observations made in the laboratory. Neither he nor those who followed him during the century after his work was published had any direct evidence for the existence of atoms. However, today we can measure the properties of individual atoms and even provide images of them. Figure 2.2. An image of the surface of silicon. The image was obtained by a technique called scanning tunneling microscopy. The color was added to the image by computer to help distinguish features. Each purple sphere is a silicon atom. As scientists developed methods for probing the nature of matter, the supposedly indivisible atom began to show signs of a more complex structure, and today we know the atom is composed of subatomic particles. Before we summarize the current model, we briefly consider a few of the landmark discoveries that led to the model. We'll see that the atom is composed, in part, of electrically charged particles, some with a positive charge and some with a negative charge. As we discuss the development of our current model of the atom, keep in mind this fact. Particles with the same charge repel each other, where particles with unlike charges attract one another. Cathode rays and electrons. During the mid-1800s, scientists began to study electrical discharge through a glass tube pumped almost entirely of air. When high voltage was applied to the electrodes of this tube, the radiation was produced between the electrodes. This radiation, called cathode rays, originated at the negative electrode and traveled to the positive electrode. Although the rays could not be seen, their presence was detected because they caused certain materials to fluoresce or to give off light. Figure 2.3. Electrons move from the cathode, which is the negative electrode, to the anode, the positive electrode. The tube contains a glass screen set diagonally to the electron beam that fluoresces, showing the path of cathode rays. Figure 2.4. Cathode ray tube with perpendicular magnetic and electric fields. The cathode rays, electrons, originate at the cathode and are accelerated towards the anode, which has a hole in the center. A narrow beam of electrons pass through the hole and travels to the fluorescent screen. The strengths of the electric and magnetic fields are adjusted so that they are fixed cancel each other, allowing the beam to travel in a straight path. Experiments showed that cathode rays are deflected by electric or magnetic fields in a way consistent with there being a stream of negative electrical charge. British scientist J.J. Thomson observed that cathode rays are the same regardless of their identity of the cathode material. In a paper published in 1897, Thomson described cathode rays as a stream of negatively charged particles. His paper is generally accepted as the discovery of what became known as the electron. Thomson constructed a cathode ray of having a hole in the anode through which a beam of electrons passed. Electrically charged plates and a magnet were positioned perpendicular to the electron beam, and a fluorescent screen was located at one end. The electric field deflected the rays in one direction, and the magnetic field deflected them in the opposite direction. Thomson adjusted the strengths of the field so that the effects balanced each other, allowing the electrons to travel in a straight path to the screen. Knowing the strengths that resulted in the straight path made it possible to calculate the value of 1.76 times 10 to the 8 coulombs per gram for the ratio of the electron's electrical charge to its mass. Once the charge to mass ratio of the electron was known, measuring either quantity allowed scientists to calculate the other. In 1909, Robert Millikan of the University of Chicago succeeded in measuring the charge of an electron by forming the experiment described in Figure 2.5. He then calculated the mass of the electron by using experimental value of the charge, 1.602 times 10 to the negative 19 coulombs, and Thomson's charge to mass ratio, 1.76 times 10 to the 8 coulombs per gram, which gave him an electron mass of 9.10 times 10 to the negative 28 grams. Figure 2.5. Millikan's oil drop experiment used to measure the charge of the electron. Small drops of oil were allowed to fall between electrically charged plates. The drops picked up extra electrons as a result of irradiation by X-rays and so became negatively charged. Millikan measured how varying the voltage between the plates affected the rate of fall. From these data, he calculated the negative charge on the drops. Because the charge on the drop was always the same integral multiple of 1.602 times 10 to the negative 19, Millikan deduced that this value to be the charge of a single electron. This result agrees well with the currently accepted value for the electron mass of 9.10938 times 10 to the negative 28 grams. This mass is about 2,000 times smaller than that of hydrogen, the lightest atom. Radioactivity. In 1896, the French scientist Henri Becquerel discovered that the compound of uranium spontaneously emits high-energy radiation. This spontaneous emission of radiation is called radioactivity. At Becquerel's suggestion, Marie Curie and her husband Pierre began experiments to isolate the radioactive components of the compound. Further study of radioactivity, principally by the British scientist Ernest Rutherford, revealed three types of radiation: alpha, beta, and gamma. The passive alpha and beta radiation are bent by an electric field, although in opposite directions. Gamma radiation is unaffected by the field. Rutherford showed that alpha and beta rays consist of fast-moving particles. In fact, beta particles are high-speed electrons that can be considered the radioactive equivalent of cathode rays. They are attracted to a positively charged plate. The alpha particles have a positive charge and are attracted to a negative plate. In units of the charge of an electron, beta particles have a charge of -1 and alpha particles a charge of +2. Each alpha particle has a mass 7,400 times that of the electron. Gamma radiation is high-energy radiation similar to X-rays. It does not consist of particles and carries no charge. Figure 2.6. Marie Curie. When Marie Curie presented her doctoral thesis, it was described as the greatest single contribution of any doctoral thesis in the history of science. In 1903, Henri Becquerel, Marie Curie, and her husband Pierre were jointly awarded the Nobel Prize in physics for their pioneering work on radioactivity, a term she introduced. In 1911, Marie Curie won a second Nobel Prize, this time in chemistry, for her discovery of the elements polonium and radium. The nuclear model of the atom. With growing evidence that the atom is composed of smaller particles, attention was given to how those particles fit together. During the early 1900s, Thomson reasoned that because electrons contribute only a very small fraction of an atom's mass, they probably were responsible for an equally small fraction of the atom's size. He proposed that the atom consisted of a uniform positive sphere of matter, in which the electrons were embedded like raisins in a pudding or seeds in a watermelon. The plum pudding model, named after a traditional English dessert, was very short-lived. In 1910, Rutherford was studying the angles at which alpha particles were deflected or scattered as they passed through a thin sheet of gold foil. He discovered that almost all the particles passed directly through the foil without deflection, with a few particles deflected about 1 degree, consistent with Thomson's plum pudding model. For the sake of completeness, Rutherford suggested that Ernest Marston, an undergraduate student working in the laboratory, look for scattering at large angles. To everyone's surprise, a small amount of scattering was observed at large angles, with some particles scattered back in the direction from which they had come. The explanation for these results was not immediately obvious, but it was clearly inconsistent with Thomson's plum pudding model. Figure 2.8. Behavior of alpha, beta, and gamma rays in an electric field. Beta rays are negatively charged and are drawn towards the positive electric plate. Gamma rays have no charge and they go straight through, and alpha are positively charged and are attracted towards the negative electric plate. Figure 2.9. J.J. Thomson's plum pudding model of the atom. You have a positive charged sphere thread throughout and with negative electrons embedded within it. Ernest Rutherford proved this model wrong. Rutherford explained the results of by postulating the nuclear model of the atom, a model in which most of the mass of each gold atom and all of the positive charge reside in a very small, extremely dense region that he called the nucleus. He postulated further that most of the volume of the atom is empty space in which electrons move around the nucleus. In the alpha scattering experiment, most of the particles passed through the foil unscattered because they did not encounter the minute nucleus of any gold atom. Occasionally, however, an alpha particle came close to the gold nucleus. The repulsion between the highly positive charge of the gold nucleus and the positive charge of the alpha particle was then strong enough to deflect to the particle, as shown in Figure 210. Subsequent experiments led to the discovery of positive particles, protons, and neutral particles, neutrons, in the nucleus. Protons were discovered in 1919 by Rutherford, and neutrons in 1932 by British scientist James Chadwick. Thus, the atom is composed of electrons, protons, and neutrons. Figure 210. Rutherford's alpha scattering experiment. When alpha particles pass through a gold foil, most passed undeflected, but some are scattered, a few at very large angles, according to the plum pudding model of the atom. The particles should experience only a minor deflections. The nuclear model of the atom explains why a few alpha particles are deflected at large angles. For clarity, the nuclear atom is here shown here as colored spheres, but most of the space around the nucleus is empty space, except for tiny electrons moving around.